Hello and welcome to this brief presentation related to the hydraulic jack. The hydraulic jack, shown diagrammatically here, has an input force applied over an inlet area of the plunger labelled here, and that produces an output force related to what's termed the area of the ram, shown here. So we will derive a relationship between the output and input force and the output and input area of our system. That's in general terms of area, and for circular section pipes we'll derive a more specific formula. It should be noted there are other presentations actually related to the topic of simple machines, but which you will see have underpinning knowledge related to this hydraulic jack presentation. There's a presentation related to levers and a presentation related to other what are termed simple machines. They just provide some background information which resonates with the contents of this presentation. So let's consider the hydraulic jack. So the basis of operation of the hydraulic jack is shown in figure 11 here. Essentially we have a force labelled as F1 here, termed the input force, or in previous presentations termed the effort, and that's applied to the inlet, which we've defined here as the plunger. So F1 is applied over area A1 of the plunger at the inlet to our system. Our output, or what we've termed our load in previous simple machines presentation, is labelled as F2 here, and that's related to area 2, the area of the ram as it's termed here. That's our output where the load is raised. So applying the input force, F1, over area A1 creates a pressure, it was P here, of F1 divided by A1. And we're assuming that the fluid used for the hydraulic jack is incompressible, some kind of oil we normally assume to be incompressible. So this means that the same pressure is applied to the larger output piston, labelled as the ram here, of area A2. So in this case the larger piston produces a force labelled as F2, which is the pressure P multiplied by area A2. But we know above that actually pressure P is F1 divided by A1, so we can derive the formula for F2 as being F1A2 divided by A1. The hydraulic jack continued. So benefits of the hydraulic jack is that large force ratios can be achieved using a small input piston. In other words, this increases the mechanical advantage, MA, what's defined as load divided by effort in our previous simple machines presentations, or basically the output force divided by the input force. So as pressure P1 at the input must be the same as pressure P2 at the output, and using our notation above we can state that F1 divided by A1 is equal to F2 divided by A2, because the pressures P are the same, both the plunger, the inlet, and at the outlet, labelled the ram here. So the forces can be shown to be in direct proportion to the areas. So rearranging the above equation, we can write F2 divided by F1 is equal to A2 divided by A1. And essentially the hydraulic jack is really another form of lever. As I said, we reviewed the lever in a previous presentation. We can write a more specific form of this formula derived here, shown here, which shows the forces are in direct proportion to the diameters. So if we know that our inlet and outlet, our plunger and our ram, have circular sections, then we can write F2 divided by F1 is equal to D2 squared divided by D1 squared. Just note I'm using the formula for cross-sectional area as pi d squared divided by 4, a formula I've used in previous presentations, where of course the capital D in the formula relates to the outside diameter shown here. This is an extract from my previous presentation. As I say, this latter formula shown here in terms of the diameter squared can only be used when we have circular cross sections at the plunger and the ram. The drawback with the hydraulic jack is that the input piston travels much further than the output piston. So in other words, force F1 moves over a longer distance than force F2. That's the work done principle we reviewed in a previous presentation. So these formulae derived here we will now use within our calculations. For non-circular areas we will use the formula in terms of forces to areas, and if we have circular sections, which in most cases we will, we'll use the formula that relates the forces to diameter squared. Here's a presentation overview. In a moment we will commence with example 4, extracted from our workbook, outline a typical solution to the type of problems we're going to consider. Then we will review exercise 15, outlined here, show the full work solution, which is essentially based on example 4. In this problem we have to calculate the value of the input force F1 to raise the stated mass of 1 ton, and also calculate the mechanical advantage of the jack. Answer stated in the bracket. And here is the approximate start time if you want to jump directly to the solution for exercise 15. Starts approximately 10 minutes into the presentation. Presentation overview continued. Then we have question 1J and question 2J, and questions 3J and question 4J. And here are the approximate start times related to question 1J, question 2J. Again, if you want to jump directly to the solutions. And the approximate start times for questions 3J, 4J. Please note these times are rounded to the nearest minute. Presentation overview continued. Then we have example 5, worked through in detail, a slightly more complicated problem. In this problem we have to determine the force required on the plunger to raise a given load, and again state the mechanical advantage. But this time we also have to calculate how many strokes the plunger would make to lift the load a given distance. Finally we calculate the power required to drive the plunger over a specific time period. So a slightly more complicated problem than the previous ones we reviewed. And here's the approximate start time to example 5, and a full work solution will be shown. Presentation overview continued. Then we have exercise 16, which essentially requires the same solution as example 5, but uses different values. And here's the approximate start time for exercise 16, but please note there is no solution included for exercise 16. Here's example 4, extracted from our hydrostatic notes. In a hydraulic jack, a force of 95 newtons is applied to the input piston, and that's to lift a load on the large output piston. If the diameter of the large piston is 200 millimeters and the diameter of the small piston is 75 millimeters, we've got to determine the load that can be raised, the output, and also state the jack's mechanical advantage, the MA. So extracting the information from the question, the input force to the piston, labelled F1, shown here, is applied to what we term the plunger here, and that's 95 newtons. The input piston diameter, labelled D1, that's associated with the area of the plunger, labelled A1 here, that's 75 millimeters, and the diameter of the output piston, D2, is 200 millimeters, and that's related to area A2 here, at what's termed the ram on our diagram. So we know from our previous derivation that F1 divided by A1 is equal to F2 divided by A2. We've got to determine the load raised, that's the output load, F2. So to rearrange for F2 we multiply both sides by A2. So F2 is equal to F1 A2 divided by A1. Now we know in the question we have circular sections at the inlet and outlet, so we can now relate force F2 in terms of diameters. So instead of the generic formula above, relating F2 to the areas of the outlet and inlet, we now can relate F2 to the diameters. So F2 is equal to F1 multiplied by diameter D2 squared, that's divided by diameter D1 squared. So to calculate the load raised at the output F2, simply insert the values, and evaluating F2 is approximately 675.6 newtons. To calculate the mechanical advantage MA, that's simply F2 divided by F1, and again inserting our values. The mechanical advantage is 7.1 to 1 decimal place. So here's a typical illustration of how we calculate, in this case, the output force, output load raised, and the mechanical advantage of our hydraulic jack. Here's exercise 15 extracted from our notes. In a hydraulic jack, force F1 is applied to the small piston to lift the load on the large piston. If the diameter of the small piston is 15 millimeters and that of the large piston is 180 millimeters, we've got to calculate the value of F1, the input force, required to lift a mass of 1 ton. We're also asked to state the mechanical advantage of the jack. Here's the answers in the bracket for F1 and for the mechanical advantage. I would encourage you to stop the presentation and attempt exercise 15, as we're informed that the input and output have circular sections, and we can use this formula here stating our relationship between the forces and the diameter squared of the plunger and ram. The full work solution is shown on the following slide. Here's exercise 15, solution. So as always, extract the information from the question. The diameter of our piston at the inlet, D1, is 15 millimeters. That relates to the area A1, shown here on a diagram for the plunger. Diameter of the ram, D2, is 180 millimeters. That's the large piston shown here. That relates to area A2. And the mass to be lifted, that would actually be on the output, is labelled as M2. It states 1 ton in the question, and of course that's equivalent to 1,000 kilograms. We've reviewed such conversions in previous presentations. So to convert a mass into a weight force using SI units, we need to multiply by gravitational acceleration. So force 2, that's the force on the output, the load we can raise, is M2 multiplied by gravitational acceleration. So M2 is 1,000 kilograms and gravitational acceleration is 9.81 meters per second squared. So that evaluates our output force, the load we can raise on the output. And referring to our relationship between forces and diameter squared here, F1 divided by D1 squared is equal to F2 divided by D2 squared. This applies to circular sections, which of course we have in this problem. The question wants us to find force F1, the input force applied on a small piston. So rearranging, F1 is equal to F2 multiplied by D1 squared divided by D2 squared. Inserting the values, F1 evaluates to be 68.125 newtons or 68.1 newtons to 1 decimal place. And the question also wants us to find the mechanical advantage, MA, which is force F2, the load raised, divided by force F1, the input force. Inserting the values and evaluating, MA is 144. So that's the solution to exercise 15. Let's now consider a few tutorial questions from our workbook. This is question 1J. A hydraulic jack has a small piston diameter of 12.5 millimeters to which a 1.2 kilonewton force is applied. We've got to determine the output force and so the maximum mass that can be raised by this jack. The output piston diameter is 7 centimeters. We also need to state the jack's mechanical advantage. Answer shown in the bracket here for the load in terms of kilonewtons, in terms of the mass and the mechanical advantage. Again, I would encourage you to stop the presentation and attempt question 1J. Again, make use of this formula we derived previously, but I'll show you the full work solution on the following slide. Here's question 1J solution. I'll let you review this at your own pace, but just be careful that the force F1 is stated in terms of kilonewtons, so be careful to account for the prefix. Also that the output diameter of the ram is in centimeters in the question, so again convert that to millimeters. This time we'll be rearranging the formula for the circular cross sections here to be in terms of the output force F2, shown here. Once we've calculated F2, That's the actual force in newtons. Don't forget we need to also calculate the mass in terms of kilograms. So that will be force F2, but divided by gravitational acceleration. So we then have our output force or output mass, stated both kilograms and tons here. And the question wants us to calculate the MA, so the MA is calculated here. That's the full solution for question 1J. Question 2J. A hydraulic jack is to be designed so that the input force of 120 newtons applied to a small piston will raise a load on the ram, that's the large piston, of 1.25 ton. If the diameter of the small piston is 2.5 centimeters, we've got to calculate the diameter of the ram to the nearest millimeter. That's required to achieve the design specification requirements. We also have to determine the mechanical advantage. Answers shown in the bracket here. Just note we are calculating the diameter of the ram, so that's the diameter of this section here. So rearrange this equation appropriately. You will need to make d2 squared, subject of the equation initially, and don't forget you have to square root to actually find the value of d2. Of course that relates to the area, A2. I would encourage you to stop the presentation and attempt this question, but the full work solution is shown on the following slide. So question 2J, here's the solution. In this question we're actually trying to find the diameter, d2, of the ram, the output diameter. I'm going to let you review the solution at your own pace, but to solve this problem we'll need to rearrange this formula here so that d2 squared is the subject. In other words, from this line here, multiply both sides by d2 squared, divide both sides by f1, and multiply both sides by d1 squared. That will then give you the formula to calculate d2 squared. And of course, to actually find d2, you will need to square root and then give the answer to the nearest millimeter. Mechanical advantage was also calculated. As I say, I'll let you review the full solution at your own pace. Here's question 3J. A hydraulic jack has a mechanical advantage of 50. We've got to calculate the input diameter of the plunger. The output diameter of the ram is 60 centimeters. Answer shown in the bracket here to 3 decimal places. So note in this question we're actually given the mechanical advantage. It's 50 to 1. So that's essentially the value of F2 divided by F1. 50. What we have to do in this case is actually find the value of D1. That's this diameter here. Again, I would encourage you to stop the presentation, attempt question 3J, but the full solution is briefly shown on the following slide. 3J, here's the full work solution. Then I'm going to let you review this at your own pace. Just notice in the question we're actually given the mechanical advantage this time, the MA. That's F2 divided by F1. Has a value of 50. So when we transpose this equation, a relationship between forces and diameter squared, or d1 squared, notice we have a ratio of f1 divided by f2. So if f2 divided by f1 is 50, then f1 divided by f2 is 1 upon 50, and that's the value that's been used here. Again, don't forget you must square root to find the value of d1. Shown here to 3 decimal places. Again, I would encourage you to stop the presentation and just think through that solution for yourself so you fully understand the process involved. Here's question 4J. I'm actually going to let you read this at your own pace. Just note in this particular question, the input section is 30 millimeters square, so no longer a round section. And we've got to calculate the output section, which of course would also be square, stating the side lengths to the nearest millimeter. Answer shown here in the bracket. So this time we'll be using the more generic formula that relates forces to areas. We will need to transpose this equation for area 2, that's the area at the output section. I encourage you to stop the presentation and attempt question 4J, but the full solution is shown on the following slide. So question 4J, here's the full work solution. As I stated on the previous slide, we're now calculating the outlet area of a square. Given the inlet area, side lengths, labelled B1 here, 30 millimeters. We need to find the value of what I've labelled B2, this dimension here. I'll let you review the solution at your own pace. The final side length for B2, the output section, is 289 millimeters. That's rounded to the nearest millimeter. As an aside, there could be an argument for rounding to 290 millimeters to actually ensure we comply with the specification and can raise the 900 kilograms, 0.9 megagrams stated in the question. But ignoring that consideration, 289 millimeters is the answer stated to question 4. Here's example 5 extracted from my notes. The plunger used in a hydraulic press has a diameter of 25.4 millimeters at the inlet, and the ram has a diameter of 10.16 centimeters, that's at the outlet. We've got to determine the force required on the plunger to raise a load of 1.25 megagrams on the ram, and also calculate the mechanical advantage of the hydraulic jack. If the plunger has a stroke of 0.15 meters, we've got to calculate how many strokes would be necessary to lift the load 0.75 meters, and then we have to calculate the power that would be required to drive the plunger if the load is lifted in 0.6 minutes. We can assume that the load's movement is continuous and any losses are negligible. So that's example 5 outlined. Let's now review the solution. As always, extract information from the question. Diameter of the plunger, D1, 25.4 millimeters. I've calculated here the area of the plunger using my formula pi d squared divided by 4. D is D1. Calculate that in terms of pi, millimeters squared. We're given the diameter of the ram in centimeters, so converted that to millimeters. And again calculated the area of the ram, pi millimeters squared. And the mass to be raised, given in the question, I've labelled that as M2 here, is 1.25 megagrams, so that's equivalent to 1250 kilograms. And I can work out the force to be raised, F2, is simply the mass multiplied by gravitational acceleration. So that evaluates to 12,262.5 newtons. That's the weight force we can raise. So reading the question, the first thing we need to calculate is the mechanical advantage. Remember, the formula for mechanical advantage is F2 divided by F1. We have F2 calculated here at the bottom of the slide. We'll need to calculate F1. We'll find F1 and then the mechanical advantage on the next slide. Example 5, the solution continued. So the first part of the question, I've labelled as part A here. We've got to find the mechanical advantage, MA. So from our formula of input force divided by input area equals output force divided by output area, rearrange for the input force, that's in terms of areas, and we know for a circular section, F1 could be stated as F2 multiplied by D1 squared divided by D2 squared. So the plunger force required F1, and we insert our values, F2 from the previous slide, as is the diameter for the input, diameter for the output. F1 evaluates to be 766.4 newtons. So we can now calculate the mechanical advantage. It's F2 divided by F1. F2 was calculated on the previous slide, F1 calculated above. So mechanical advantage is 16. Example 5, solution continued here. I'll call this part B. We've got to calculate the number of strokes required, I've labelled that capital N here, to raise the load. So let's think this through. Step number 1 here. Firstly, I'm going to find the volume of the fluid to be moved in raising the ram 0.75 meters. That was stated in the question, i.e. to lift the load 0.75 meters. That's the ram. So the volume of fluid, I've labelled that V2 here, that has to be moved on the output side is the area at the output, A2, multiplied by the distance moved by the fluid at the output, S2. So we can calculate V2, A2 is from the previous slide, S2 in millimeters here, 750 millimeters, is used to calculate V2, pi millimeters cubed here, and then part 2, as I've labelled it here, the plunger movement in one stroke is stated in the question as 150 millimeters. That's stated here, the plunger at a stroke of 0.15 meters, that's my 150 millimeters. So to calculate the volume of fluid moved in one stroke of the plunger, call that V1 here, that will be A1 multiplied by S1, area at the inlet multiplied by the movement of the inlet in one stroke. So V1 can be calculated from the A1 on the previous slide multiplied by 150 millimeters. That gives us the volume of fluid moved per stroke. So to calculate the number of plunger strokes required, capital N here, is simply V2 divided by V1. Inserting the values, notice I've ignored the pi value because of course that cancels top and bottom. Number of strokes required on the input is 80. Again, you see the slight disadvantage of this system is that the movement on the plunger side, the input side, is very significant to raise the load on the output side. Example 5, solution continued. What I've labelled as part C here, calculate the power, capital P, required to lift the weight or the load in 0.6 minutes. Just note for reference that the time taken here needs to be calculated in seconds, so 0.6 multiplied by 60, that evaluates to 36 seconds, is the time duration. So the power required is the force at the output multiplied by the distance moved at the output, F2 multiplied by S2, and that's all divided by the time taken, lowercase t here. Inserting our values, the power required evaluates to 255.5 watts to 1 decimal place. That's the solution for example 5. And finally I'll leave you with exercise 16 to attempt at your own pace. Given the information, so part A, firstly we have to calculate the force required on the plunger to raise a mass of 1 ton on the ram. Part B, given the plunger's stroke, we've got to calculate how many strokes the plunger makes to lift a 1 ton load. And part C, neglecting losses and assuming the weight moves continuously, we've got to determine what power is required to drive the plunger if the weight or the load is lifted in 2 minutes. The answers are shown in the bracket here. So I'd encourage you to now attempt exercise 16. It's based around the solution for example 5 we reviewed on the previous slides. A reference here is the bibliography used to help generate these fluid mechanics presentations, and I hope this presentation has been of use to you, and as always, thank you for viewing.